So this was pretty revolutionary, and it modeled what was happening with scientists in the physical world trying to understand the nature of light, right? For 100 years, they thought that light was traveling as waves, and then Einstein comes along and says, wait, it also can behave as a particle. There's a duality there. And we're seeing the same thing with the electron, okay? And so the reason that this work was so revolutionary is because now it allowed scientists who were studying the atom to start thinking about, well, what if the electron really does behave like a wave? We can maybe make some new predictions and new models that do a better job of explaining the observations that were made. And that's exactly what happened. It paved the way for over the next 10 years, 10 to 20 years or so, for even more research to be done, now considering what happens if the electron behaves as a wave. There's a lot of names on here. Again, this is just more for historical purposes. You've probably heard of some of these names: Heisenberg, Schrodinger. You might not have heard of Max Born. All right. It's not a history class, but I want to tell you about some of their contributions because it was pretty important. Maybe you've heard of the Heisenberg uncertainty principle. You can't measure both the position and the momentum of an electron at the same time. You can measure one, but you can't necessarily measure the other. And there's some descriptions of that up here. On the left-hand side, basically the energy required to be able to see where an electron is. If you had a magic microscope that was so powerful that you could actually see an electron, the power in observing it is greater than the energy of the electron. So the actual act of looking at it pushes it somewhere else. So you can never really ever see where the electron is, okay? Now, formally stated as the Heisenberg uncertainty principle is over here, right? You cannot simultaneously know the exact position and the exact momentum of an electron, although you can measure each of them separately. You just can't know where they are at the same time. Pretty much what that means is you never really know where the electron is, okay? You never know exactly where the electron is at any time. But what you can do is you can predict where it might be at any given time. Where it could be. In other words, we can define a probability region of where these electrons could be found at any given time. Now, from that idea, we have Erwin Schrodinger, who came up with this really fantastic and crazy mathematical interpretation of where we actually can describe where electrons could be found at any given time, even though we can't actually see where they are. But this was, again, treating an electron as a wave, right? So let's put that at the top. This is all now considering electrons as wave, behaving as a wave, okay? Not as particles. Okay, so don't worry, we're not going to get into this crazy math, all right? I'll just say it's crazy math. But really what we're looking at is wave functions in 3 dimensions, the X, the Y, and the Z dimensions. So these are all wave functions in 3 dimensions. And the wave function itself is this Greek letter here, psi. Right? Those are the wave functions. Now, again, we're not going to be using this equation, but when you solve the wave functions using this equation, you can now define what we call quantum numbers. In fact, solving these wave functions gives us the first three quantum numbers. There's four quantum numbers in total that we're going to describe today, okay? But the first three come from solutions to the Schrodinger wave equation. So solutions to the Schrodinger wave equation gives us the first three quantum numbers, and we're going to be describing these in a moment, all right? But these are mathematical descriptions of the electron behavior. As waveforms. Right? These are these matter waves that De Broglie had envisioned in his 5-year or 5-page PhD thesis. Right? So these psi, this wave function, this is essentially De Broglie's mass waves. You can think of them the same way. And what you'll see is that these first three quantum numbers, they're going to basically describe the unique position of electrons within an atom. Each electron within an atom. Now, usually in this class, I don't like to just describe things and tell you things for you to memorize moving forward. I try to give you an understanding of the underlying synthesis of why these rules and definitions and principles exist. When it comes to the quantum numbers, I just can't do that because it's going to require then solving all the crazy math and showing you where all these numbers come from. And that's so far beyond the scope of this class, all right? So what's going to come up on the next slide is a description of these quantum numbers and how they are used to describe the electrons within an atom. But you just have to accept that those are the rules that come from the solutions to the Schrodinger wave equations, okay? Now, before we do that, there's one more thing to describe, right? And that's going to be the contribution from Max Born. So because of all this probability now, we no longer have electrons in orbit the way we used to draw it with the Rutherford model, all right? Electrons are no longer in orbit. Instead, Max Born's contribution was recognizing that if you took the square of the wave function from Schrodinger's solution, just square it, you would be defining a three-dimensional region of probability of where these electrons could be found. All right, this is going to be a three-dimensional probability space where the electrons could be found. So it's kind of like electrons in orbit, but we can't see them anymore. So instead we define the area of probability, and the word that was used for that is called the orbital. It sounds like an orbit, right? Because that's where it comes from, but this is what an orbital is. And we're going to be talking a lot about orbitals when we talk about quantum theory. Electrons are no longer in orbit, but we can describe the orbitals that the electrons are in. Okay? So buckle up. We're going to go to this mostly blank slide, and I'm going to define the rules for you for these quantum numbers. I'm going to try to go slowly. Now, I told you we have 4 quantum numbers overall that we're going to describe, but the first 3 come from the solutions of the Schrodinger wave equations. The first quantum number 1, is what we call lowercase n. And we can easily define n as simple whole integers. These are all whole numbers, by the way, or integers, I should say. So this is going to be n is equal to 1, 2, 3, 4, and so on. Okay? This is the same 1, 2, 3, and 4 that we looked at in the Bohr model. As the number increases, we're increasing the energy level. Okay? As we increase the number here, we're increasing the overall energy level. So increasing E, let's just say energy. And as also shown in the Bohr model, if you recall, when we went from n equals 1 to n equals 2 to n equals 3, those orbits in the Bohr model got further away from the nucleus. Right? That's another trend we're going to see. The electrons are also going to be further from the nucleus. All right, so that's the principal quantum number. We also call that the principal energy level. And sometimes people also refer to this as shells, because we're going to be building shells within shells within shells as we get in larger principal energy levels. The electrons are further away from the nucleus. Okay, so sometimes we talk about these as shells. So I'm just going to offset that in a different color so you get an idea of the words that we use to describe the same thing. So principal energy level, or we might call this the principal shells. Now you'll also find that the principal quantum number corresponds to the rows of the periodic table. So if we're talking about electrons at n equals 1, we're describing electrons that you would find in helium and hydrogen. If we're at principal energy level 2, we're talking about electrons that are in the elements of lithium, sodium, boron, carbon, et cetera, et cetera. Okay, so the principal energy level also corresponds to the rows of the periodic table. Here, I can make this a little bigger for you guys. How's that? That's a little better, probably. Okay, so that one's pretty simple. Now, when we talk about the second quantum number, this is what we call the angular momentum quantum number. It's sometimes called the azimuthal, but I'm not going to write that down for you because your textbook doesn't use that term. All right, so we're going to call this the angular momentum quantum number. We use a cursive L for this number. Okay, let me move this up a little bit here. So numerically, L, this is also going to be integers. And in this case, the integers start at 0 and they go all the way up to n minus 1. Okay, so that means 0, 1, 2, 3, 4, what have you, but we stop at n minus 1. Now that might seem strange at first, but when I start describing these in a moment here, it will start to make a little bit more sense. Right? So, for example, when we're at n equals 1, so if the principal quantum number is 1, okay, then what possible values would we have for L? L is equal to integers 0 up to n minus 1. So if n equals 1, what are the possible values for L? Just 0, right? Because 0, that's n minus 1. So we stop at 0. Okay? If we're at the second principal energy level, n equals 2, what possible values do we have for L? We have 0 and we have 1. So there's two possibilities, right? So L can equal 0 or L can equal 1. When n equals 3, L can be equal to 0, 1, or 2. We just keep counting up until you get to n minus 1. When you get to n equals 4, we have now 4 possible values for L: 0, 1, 2, and 3. And I should emphasize, these numbers aren't just made up, okay? These come from solutions to the Schrodinger wave equations. When you solve to try to describe those different waveforms in the 3 different dimensions. All right, now, instead of counting by zeros, ones, twos, and threes, which is what we're going to do in this lecture, moving forward, we're going to use a little easier system to describe L equals 0, L equals 1, L equals 2, and so forth. And this is probably what you all remember when you took this in, say, high school, or the last time you took an introductory chemistry class. Instead of L equals 0, we're going to call this the S sublevel. When L equals 1, we're going to call that the P sublevel. So this is going to be the S or the P sublevels. When L equals 2, that's going to be the D sublevel. So this will be S, P, and D sublevels. And finally, when we have L equals 3, we call that the F sublevel. So we have S, P, D, and F sublevels. Okay? So it's just a different terminology to describe the same thing. We're just not going to deal with the quantum numbers like that. Now, these are all called sublevels. These are all within the principal energy level. So notice that all 4 of these have an S sublevel, but there's an S sublevel at the n equals 1 principal energy level. There's a different S sublevel at n equals 2. And there's yet another S sublevel that belongs to n equals 3, and so on and so forth, okay? So that's why these are sublevels. These are shells within shells, okay? So the angular momentum quantum number, this describes the sublevel. And sometimes, instead of sublevel, we might call these subshells. So you'll see that as well. And you may even see me say these terms interchangeably as well. Sublevel, subshell. They mean the same thing. These are the sublevels: S, P, D, and F. Now, everything's going to be described as increasing energy levels. We always are going to start at the ground state, and we're going to build ourselves up, okay? So within a given principal energy level, so within a given n, you will find that the S sublevel is less energetic than the P sublevel. The P sublevel is less energetic than the D, and so on and so forth. So in other words, we have an increasing energy level here as well. That's within an n, okay? So if we're at n equals 3, okay, the 3s sublevel is less energetic than the 3p sublevel, and then comes next the 3d sublevel. But that doesn't mean that the 3d sublevel is more or less energetic than the 2p. I mean, it may be, but I'm just saying, this idea of increasing energy level is within a given principal energy level. So within a given shell, these subshells increase in their energy level. Does that make sense? Am I going slow enough? Good. Anyone wonder where this S, P, D, and F comes from? Does anybody know? Journey back with me to last lecture. Remember these Fraunhofer lines that we talked about? And I told you for, what, like 50 some odd years, they were spending a lot of time characterizing these dark lines in the spectrum, mapping them very, very carefully. Well, they started using words to describe some of these lines. Some lines look a little bit different than others. Make sure I get this right. Some of the lines were identified as being sharp lines. Some of them were called principal lines. Some of them were diffuse. And some of them were also called fundamental. These were all terms that were used to describe these dark lines. S, P, D, and F. That's where it comes from. It's a little bit of trivia for you. Next time you're with your friends, you can impress them that you know where S, P, D, and F names comes from. But that's not in the textbook. You got to go find that somewhere else. So that's a little tidbit for you. And yeah. Okay, so now let's talk about the third quantum number. So the first one describes the period, the principal energy level, so the period on the periodic table, the row, I should say, on the periodic table. The second one describes the subshell. The third quantum number is going to describe the orbital. Now, I already told you what an orbital is, okay? And this, again, comes from a solution of the Schrodinger wave equations. Now, this one's going to get a little bit more complicated, all right? So let me just give us more space to work with here. As far as the numbers and how we use them, this is M sub L. This is also called the magnetic quantum number. But it's M sub L. The number is going to depend on what subshell that we're in, okay? And we're still going to use integers. But now the integers, they're going to range from minus L to plus L, and they're going to include 0. All right, so if L is 3, we're going to have -3, -2, -1, 0, +1, +2, +3. If L is equal to 1, then we're going to have -1, 0, +1. All right, and so it's integers from negative, whatever L is, to positive, whatever L is, and include 0. But let me show you that now in examples. And let's just go through each of the 4 principal energy levels. Let's just map this out. So when n equals 1, we already know that there's only one subshell, L equals 0, right? And that's what we call the S sublevel. I'll just remind you of that. Now, for M sub L, let me just put a heading up here, M sub L. So when L equals 0, there's only one value for M sub L because there's only one value for L. So when M sub L equals 0, or let's just say at M equals, or M sub 0, let's call it that way. At M0, now using these rules, what are the possible values for M sub L? It's just 0. That means that when we're at L equals 0, when we're at the S sublevel, there's only one orbital. At the S sublevel. All right, when you solve the wave equations for n equals 2, you get 2 values for L. You have L is equal to 0, and you have L is equal to 1. Well, we already know that when L is equal to 0, so M sub L, so when it's 0, that's 0. And when L is equal to 1, so M sub 1, as I told you, now we have 3 values for M sub L. That's going to be -1, 0, and +1. Okay. So remember, L sub 1, that's the P sublevel, right? So this means that at the p sublevel, we have we have 3 orbitals. Everyone still with me? All right, now let's go to n equals 3. We've got 3 values for L. L is equal to 0, L is equal to 1, L is equal to 2. When L is equal to 1, we only have 1 orbital there. Sorry, when L is equal to 0, my mistake, we only have 1 orbital. When L is equal to 1, we have 3 orbitals, -1, 0, +1. When L is equal to 2, we now have 5. We have -2, -1, 0, +1, and +2. All right, so this is at the D sublevel. Okay, we have 5 orbitals. And I'm not going to repeat the first 3. I'll just take you one more level here. Okay, at n equals 4, everything else is the same, except now we also have the L equals 3 sublevel. That's the F sublevel. So when we're at M sub 3, we're going to have -3, -2, -1, 0, +1, +2, +3. Okay, so that's the F sublevel. We have 7 orbitals. Okay. We pause for a moment to make sure you get everything nice and neat here. But like I said, this is also going to be posted for you. Now, back to this idea of increasing energy level. We're always building up from the ground state, okay? And as we're increasing in our principal shells or our sublevels, we're always going up in energy level. But now when we get to the orbital, it's a little bit different, because now at any given p sublevel, we have 3 orbitals. At any given d sublevel, we have 5 orbitals. These are all of equal energy. They're not increasing energy. Those 3 are all the same. They specify the same energy level for the electron. And you have a feel for what that energy level means now, because we talked about the light that's either absorbed or emitted as electrons go to one energy level or another in an atom. Well, these are the energy levels that we're talking about, not just the principal that it's jumping to, that shows in the Bohr model, but now we've got sublevels and orbitals that these electrons, that's where they exist. But where they exist in the orbital is a region of probability, okay? But it still is defined by a specific energy level as well. So unlike the trend before, okay, these 3 orbitals, these all specify equal energy. It's what we call degenerate orbitals. And what's important about degenerate orbitals is, although they're still in the same energy level of the atom, so they each one defines its own area of probability. They don't overlap. So these are non-overlapping regions of probability. But they're all at the same energy level. Here, let's highlight that. It's so important. They're non-overlapping. If I were to take this lecture hall and say this lecture hall is one of our energy levels. So if there's an electron in this lecture hall, it is at its own specific energy level, okay? But if it's in a p, if this defines the p sublevel, well, there's three of them. There's three orbitals here. So I can divide this room into three equal parts. And that electron could be maybe on the left-hand compartment. But if it's in the left-hand side, it only exists in that 1/3 of the space. It will never be found in the other 2/3. The same is true for an electron that might be in the center place. It can exist anywhere probabilistically in that third of the orbital of the sublevel, but it will never be in the regions of space defined by the other two orbitals, even though it specifies the exact energy level, the exact same energy level. Okay, now that's going to be true for the D sublevel orbitals as well, right? There's 5 of them, but those are all equal energy. So you have 5 degenerate orbitals there. If we're talking about the F sublevel, we're going to have 7 degenerate orbitals, but it's the same idea. Okay, so those are the first 3 quantum numbers. All right, there is one more quantum number though, number 4, but that does not come from the solution of the Schrodinger equations. This comes from subsequent studies, and I'm not going to go into a lot of detail. I'll just show you very briefly some of the things that were found. Okay, like for example, looking back at the spectral lines. I don't know if it's going to show up here or not, but remember I just defined for you. Some were labeled sharp, some were labeled diffuse, right? Principal and fundamental. Well, take a look at that red one. Okay, that might not be one line. If you look at it very, very carefully, they actually found that there were some doublets. Here, let's put that in red since this is a red line. What they thought was a single line might be more than one. Maybe this was one of the diffuse lines that when you look more carefully, there's actually 2 in there. Another experiment, we take a beam of silver atoms and turn them into ions and put them through a magnetic sector, okay? You can actually separate 2 different beams from what they thought was one, okay? And they're gonna call these different magnetic spins, because even though we're thinking about electrons as waves, we also can think of electrons as particles. There's a wealth of experimental data that shows that electrons also behave as particles. And those particles have a charge, which is a negative charge, okay? Now, for you physicists out there, you might know what happens when you take something that's charged and move it. Does anybody know? What happens when you take a charged particle and you move it? What do you form when you do that? Anybody know? You make a magnetic field, all right? So things that are charged that move in space form magnetic fields. And that's what they can measure, all right? We have magnetic fields here. You can separate 2 different, what we're going to call magnetic spins. Now, we call these spin up and spin down, but that's just by convention, okay? We can detect that there are 2 things in here for every orbital is what this comes down to. All right, so every orbital actually contains 2 electrons. And, or I should say up to 2. Because it could contain just 1, but it won't contain more than 2. And we can actually measure these as different magnetic spins. What we call spins. I'll put that in quotation marks. And the terms that we use is we arbitrarily call one of them is spin up, and the other one we call spin down. But it's not that one's actually going up and one's going down. We're just arbitrarily defining one, and by doing so, the other one's going to be in the opposite direction. It was Wolfgang Pauli who actually came up with this idea that we now call the Pauli exclusion principle, because now we have these 4 quantum numbers, And we can use them to demonstrate that even though we don't know where the electrons are, no two electrons can ever be at exactly the same place at the same time. That's the way I like to talk about it. It says it right here. No two electrons can share the same. Oh, no, that's Pauli's actual definition. No two electrons can share the same set of 4 quantum numbers. That's the same as saying cannot exist in the same place at the same time. Even though we don't know where they are, they can't be at the same place at the same time. Meaning that if we were to look at the 4 quantum numbers that would describe the unique position of an electron in an atom, those sets of 4 quantum numbers will always be different. You could make a separate address, so to speak, for each electron in an atom. We're not going to do that in this class. I don't really see the need for that. The textbook will take you through that a little bit if you're really interested. But we're going to be working with defining the electrons using the S and P and D, and we're going to use some other symbols. We're not going to use the 4 quantum number addresses for them, all right? But I do want you to understand what those 4 quantum numbers represent and where they come from. So spin up, although I may say spin up, we're going to be using different symbols. We're going to use an up arrow for spin up, or sometimes I'll just write that as a half arrow. And spin down, we're going to have a down arrow, or maybe a half arrow. Now, as far as the quantum numbers are concerned, though, instead of integers, we use +1/2 and -1/2. So spin up is +1/2 and spin down is -1/2. So when you see them as quantum numbers, and here you can see it written, -1/2 and +1/2. And again, I will refer you to the textbook to go a little bit deeper into how we use those addresses. So for example, you might have a quantum number that looks like 1, 0, 0, +1/2. And you can interpret that in order, right? This is the principal quantum number, so we know that we're at n equals 1. So right now we're describing an electron that's only in that first energy level. And at that first energy level, there's only one sublevel. So if the first one is 1, the second one has to be a 0. It can't be a 1. Because if you look back at those rules, at n equals 1, there's only one sublevel, and that's 0. If you're 0, then the third quantum number also has to be 0. Because at L equals 0, there's only one orbital. That's what we designate as 0. But within that orbital, we have up to 2 electrons. One will be +1/2, the other one will be -1/2. And so on. Like I said, I don't want to really spend too much time on using these as addresses, but I wanted to show you just a couple of examples of how it's used. Here, I'll show you one more. Let's say we have an electron at n equals 3. Well, we have different choices of what now the second quantum number could be following those rules. That second one could be a 0, it could be a 1, it could be a 2, but it won't be a 3, it won't be a 4, right? That can't exist based on the solutions to the Schrodinger wave equations. Okay, so let's just say that one's at 2. If I were to say that's the electron we're talking about, now we're at sublevel 2. So now you think, okay, well, how many orbitals can there be at sublevel 2? You could have -2, -1, 0, +1, +2. Any of those can be in that third position. So let's say I'm talking about an electron that's at the -1. That's fine. And then there's an electron in there. It's either going to be spin up or spin down. So you might see it like this. Okay. There's maybe 1 or 2 problems in the homework set that kind of just have you practice on looking at these and defining, well, which set of 4 are possible or which set of 4 are not possible. For example, one that wouldn't be possible would look like this. One, I already gave you that example. Let's see. 2, 3, 0 plus 1/2. That can't exist if you look back at the rules, because 3, right, the sublevel 3 can't exist at n equals 2. There is no 3 sublevel at n equals 1. If you go back to the rules, you'll see that, okay? So there's another trend that you see up here, okay? At n equals 1, there's only the S sublevel, and that's it. But at n equals 2, we have an S sublevel and a P sublevel. At n equals 3, we have S, P, and D. At n equals 4, we have S, P, D, and F, okay? So as you build larger and larger principal energy levels, you also have the same number of sublevels in there as well. And now we know that there's 2 electrons in each sublevel. So let's put that in here now. Let's start building this up. So at n equals 1, okay, we only have an S sublevel. And at the S sublevel, there is only 1 orbital. So how many electrons total can we have at n equals 1? Only 2. There's only room for 2 electrons at n equals 1. And if we have to describe an atom that has more than 2, we've got to put those additional electrons now into the next higher energy level. We're always building up from the ground. So we start at n equals 1, and then we add more and more electrons into the higher energy levels if we need to. So at n equals 2, so here, n equals 1 just encompasses here. At n equals 2, what do we have? We have an S sublevel and we have a P sublevel. So n equals 2 has both of those. Now at the P sublevel, how many orbitals are there? 3. So how many electrons can we have total at the P sublevel? 6. There's room for 6 electrons at the P sublevel. If I go to n equals 3, now that's going to include the D sublevel. Okay, there's 5 orbitals at the D sublevel. So how many electrons can we fit into the D sublevel? We could fit 10 electrons. So overall, at n equals 1, we can have a total of, here, I need to move this over just a little bit. Didn't leave myself enough room in the margins here. We have room for two electrons total. At n equals 2, we have room for how many total electrons at that principal energy level? 8. And how about at n equals 3? 18. You're getting the hang of it. Okay. Now, nothing up my sleeve. Okay. And presto, here's the periodic table with its funny shape. Okay. Why is it this funny shape? This shape is based on what we know about electron structure from quantum theory. Okay. I mentioned that the rows, that corresponds to the period. So the principal quantum number that corresponds to the rows. So 1, 2, 3, 4, 5, 6, 7. Now you notice that we have some taller columns on the left and taller columns on the right. Okay. Now I'm not going to include hydrogen and helium here. Those are slightly special cases in the far as this organization goes. But if you notice on the left-hand side, okay, if I were to just circle in red here, this area where we have the 2 tall columns, we have at each principal energy level, we have 2 spots. We have 2 boxes. Think of an electron goes into each box, because we know now that the atomic number, that's the number of protons. So as we increase from lithium to beryllium, we're adding 1 proton. And if these are neutral, if we add 1 proton, we're adding 1 electron. So just think of adding an electron to each box. When we come back to sodium and magnesium, it's the same idea here. potassium, and calcium. These are going to define the electrons where they are in the S sublevels at each principal energy level. This is what we call the S block. In the S block, there's room for 2. Over here on the right-hand side is where we're going to have electrons as we place them building up. Okay, we will start at 1, and we go to 2, and so on, and we fill in at each level. We go to S, and then we go to P. And the most energetic electron, the last one that you place, okay, if it's at a P sublevel, it's going to be from an element that comes from this section of the periodic table. This is what we call the P block. And notice that there are how many boxes in each row of the P block? 1, 2, 3, 4, 5, 6. There's room for 6 electrons. How many electrons can P hold? 6. So what I'm doing here is I'm saying where the last electron is placed as you're building up. So as building up from the ground state, this is going to be where the last electron is placed. And if you place it in a P sublevel, then the element that you're defining, that's where you're going to find it on the periodic table. It's organized based on the quantum theory. When you get to the transition metals in here, this is going to identify, or sorry, this is going to be if the last electron is placed at a D sublevel, those elements are going to be in this area, in the transition metals. So this is the D block. How many electrons can you hold in the D block? 10. Don't count them. How many boxes do you suppose are across there? There's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The inner transition, how many sublevels, sorry, how many orbitals are there at the F sublevel? 7. How many electrons can the F sublevel hold? 14. So how many boxes do you suppose are across here? 14. This is why the periodic table is shaped the way it is. It's based on what we just covered today, the organization of the electrons in the atom as defined by quantum theory and solving the Schrodinger wave equation. Okay, so there's 14. So hopefully that will unlock the mystery of why the periodic table is shaped this way. And once you realize that, you can now, instead of having to memorize all those rules about, well, how many are at this level and how many are at that level, where do you have S and where do you have P? If you remember this organization, S blocks, P blocks, and D blocks, with a little bit more explanation that we'll do on Monday, you'll see that you don't need to memorize any of that. You'll always have a periodic table in front of you, and that will be your roadmap to actually understanding and remembering all of those quantum theory rules that we just talked about today. Okay? I know this is real complicated stuff, but now that I've brought you to the quantum brink, okay, we'll come back now to reality next week, and we'll start using a little bit more easy way to account for where the electrons are and to start to understand how that works with chemical reactions.